Looking at similar triangles, first we'll take a look at the blueprint or architectural drawing for a house. So compared to the actual house, these drawings, the blueprint or an architectural drawing, are similar but not equal in size to the actual house. It is a proportional representation of what the house will look like. It's scaled down on a piece of paper so that people can follow the measurements and the architectural features in order to build the house. So you can see that this blueprint or this architectural drawing would be prepared to be able to create a similar figure or a similar representation of the house, in this case the actual house itself. It's the same when looking at similar triangles. If we had two triangles such as these two, we would say that if they were similar triangles that the side lengths would be proportional. So this side length would be some enlargement of this side length, and that enlargement would be true for all of the sides of the triangle. So they would be scaled either up or down, but certainly they would be similar in their appearance and in all of their angle measurements. Let's take a closer look at similar triangles. We can see that similar triangles are the same shape but not the same size. And we have two triangles here. First one will be triangle ABC. You can see the side lengths identified on triangle ABC. And we've got triangle DEF over here. Again, side lengths are identified. For these two to be similar triangles, it would mean that the corresponding angles in each of the respective triangles would be congruent. They would be the exact same measure. So this angle measure in this triangle, in the first triangle, would be the exact same as this angle in the second triangle. The measure of this one here in the first triangle would be the exact same measure as this one in the second triangle, followed by the third one in this triangle would have the exact same measure degrees as this one in the second triangle. Also, we would have to take a look at the side lengths. And the side lengths in similar triangles would be in some sort of ratio, that the corresponding sides in the first one compared to the second triangle would be in a ratio. The ratio is called the scale factor. So what you would do to this measure in order to get the value in its similar triangle or its corresponding side in the second triangle. Can you spot what the scale factor would be in this illustration? Scale factor, if we take a look at the corresponding sides, this side here and its corresponding side in the second triangle, the values 2 and 4. How are those related? Take a look at the next pair of corresponding sides, 5 and 10. And the last pair, 4 and 8. Perhaps you might be able to identify that in the first triangle, if we take these measurements and we double them, we get the measurements in the second triangle. So we call this a scale factor of a 1:2 ratio. Or it can also be written in reverse. If we deal with the second triangle first, it could be a 2:1 ratio. This identifies that these are similar triangles in a 2:1 or a 1:2 ratio because the first triangle, if you double all of the side lengths, the corresponding sides, you'll get the second triangle, all of the measurements there.